There are places on Earth where the planet speaks in whispers, islands so remote that the horizon seems endless. Waters so deep that sunlight fades long before reaching the ocean floor. And beneath it all, a silence that has persisted for centuries. But silence, as we have learned, is not the same as stillness. In the kingdom of Tonga, roughly 65 kilometers north of the capital Nuku'alofa, two small islands rose from the sea long ago, Hunga Tonga, Hunga Haʻapai. Their names, spoken softly by generations of Polynesian navigators, carried the weight of ancient respect. These were not mountains born of majesty. They were remnants, fragments of a volcanic caldera that had once roared and then retreated beneath the waves. What remained above water was modest two crescents of volcanic stone, separated by a shallow channel barely noticed by the wider world. For decades they rested. Fishermen passed by. Seabirds nested on their cliffs. The sea moved around them as it always had, patient and eternal. But beneath the surface, something ancient was stirring. The earth, you see, does not forget. It remembers every chamber of molten rock, every fault line, every place where the crust grows thin and the mantle presses upward, waiting. Hunga Tonga Hunga Haʻapai sat atop one of the most geologically restless regions on the planet, the Pacific Ring of Fire. Here, the Pacific Plate slides beneath the Indo-Australian Plate in a process geologists call subduction. It is a collision measured not in seconds but in millennia. And from that collision, volcanoes are born. Most of the time, these forces operate beyond human perception. Mountains rise at the speed of fingernails growing. Magma chambers fill over centuries. The Earth works on a timescale we rarely understand. But sometimes the Earth accelerates. In late 2014, the first sign came, not with violence but with a slow emergence. Between the two islands, the ocean began to boil. Steam rose into the tropical air. And then, day by day, something new appeared. A third island. Born from underwater eruptions, it rose steadily, bridging the gap between Hunga Tonga and Hunga Haʻapai. By January 2015, the three had become a single landmass where there had been open water. Scientists watched with fascination. This was creation in real time. A rare opportunity to witness the Earth building itself, grain by grain, eruption by eruption. The island stabilized. Vegetation began to take root. Researchers visited, collected samples, documented the transformation. It seemed perhaps that the volcano had spoken its piece. But creation and destruction are not opposites in the language of volcanoes. They are siblings. 7 years after that first emergence, in the final days of 2021, the silence broke again. Small eruptions. Plumes of steam and ash rising a few kilometers into the sky. Nothing extraordinary by volcanic standards. The Smithsonian Global Volcanism Program noted the activity. Alerts were issued. Monitoring stations recorded the tremors. And then, on January 15, 2022, at 4:15 in the afternoon local time, the Earth stopped whispering. This is a story shaped by time and patience, by forces older than memory and powerful beyond imagination. If you choose to remain with us, the Earth is about to reveal one of its most extraordinary transformations. Welcome to Fury of the Earth. The ocean, from above, appears deceptively simple. A vast expanse of blue. Waves following wind. Islands scattered like forgotten thoughts across an ancient mind. But beneath that surface lies a different world entirely, a landscape of mountains and trenches, valleys deeper than any on land, and volcanoes that dwarf their terrestrial cousins. Hunga Tonga Hunga Haʻapai was never just two small islands. It was the visible tip of something far larger. A volcanic edifice rising nearly 2 kilometers from the seafloor, with a submerged caldera, a collapsed volcanic crater stretching 5 kilometers wide beneath the waves. What we saw above water was merely the rim, the broken edge of an ancient explosion that had hollowed out the mountain's heart long before human memory. The Tonga Trench, lying just to the east, descends more than 10 kilometers into the Earth's crust. Here, the Pacific Plate, a vast slab of oceanic crust, pushes beneath the Indo-Australian Plate at a rate of roughly 24 centimeters per year. It sounds modest, less than the length of a human foot annually. But over millions of years, entire ocean floors have been consumed. Dragged down into the mantle where rock becomes molten once more, and the cycle continues. This process subduction is what builds volcanic arcs. As the descending plate reaches depths of 100 to 150 kilometers, it begins to melt. Water trapped within the minerals lowers the melting point of surrounding rock. Magma forms less dense than the solid stone around it and begins its slow ascent. It rises through fractures, collects in chambers, waits, sometimes for centuries. The magma beneath Hunga Tonga was not a simple pool of molten rock. It was a complex mixture basaltic in origin, but enriched with volatile compounds. Water vapor, carbon dioxide, sulfur dioxide. These gases, dissolved under immense pressure, were what made the system dangerous. Think of it as champagne in a bottle. The liquid is calm, but the moment pressure releases, everything changes. By late 2021, something had shifted in the delicate equilibrium beneath the volcano. Magma was rising. Fresh molten material pushing into chambers that had been relatively stable. The pressure was building, but slowly, gradually enough that the early eruptions in December remained modest. Steam and ash vented through the existing crater. The system was releasing tension, like a valve carefully managing pressure. But valves can fail. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. What scientists monitoring the volcano could not see, what satellites and seismographs could only hint at, was the volume of magma accumulating beneath the caldera floor. The submerged crater, flooded with seawater, sat directly above one of the magma chamber's weakest points. When molten rock at temperatures exceeding 1,000 degrees Celsius meets seawater, the reaction is not gradual. Water flashes to steam instantly. The volume expands by a factor of 1,700 in milliseconds. This is called a phreatomagmatic eruption. It is one of the most violent volcanic phenomena known to science. Throughout early January 2022, seismic activity continued. Small earthquakes clustered beneath the volcano. Gas emissions increased. The patterns were concerning but not unprecedented. Volcanic systems are notoriously difficult to predict with precision. Some awaken slowly over months or years. Others transition from minor unrest to catastrophic eruption in hours. Hunga Hunga Haʻapai had shown both tendencies in its recent history. The slow birth of the new island in 2014 and now, in January 2022, something different. The tremors were deepening. The intervals between small eruptions were shortening. And beneath the caldera, where ocean water had seeped into fractures and porous volcanic rock over years, a network of superheated pathways was forming. The stage was set. On the morning of January 15th, the volcano produced several moderate explosions. Ash plumes rose to heights of about 15 kilometers. Impressive, certainly, but within the range of what had been observed in previous days. Satellite imagery showed the plumes drifting westward on the prevailing winds. Scientists continued their observations. There was concern, but not alarm. The Kingdom of Tonga had experienced volcanic eruptions before. Protocols were in place, coastal communities were aware. The volcano was remote enough that direct danger to population centers seemed limited. What no instrument could measure in those final hours was the critical threshold forming below. The point at which pressure would overcome all resistance. The moment when the Earth would stop releasing tension gradually, and instead, release everything at once. That moment arrived at 4:15 in the afternoon. And when it did, the sound would circle the entire planet. There are events in nature that defy comfortable description. Earthquakes that rewrite coastlines in seconds. Tornadoes that erase entire towns from the landscape. Tsunamis that arrive with the weight of the ocean behind them. But volcanic eruptions operate on a different scale of power. They do not merely move through space, they alter it. They inject millions of tons of material into the atmosphere. They generate their own weather systems. They can, in rare moments, affect the climate of the entire world. What happened at 4:15 p.m. on January 15th, 2022, was one of those rare moments. The eruption began beneath the waterline inside the submerged caldera. Magma had finally breached the weakest barrier, and seawater flooded into direct contact with molten rock at incomprehensible temperatures. The resulting explosion was not merely volcanic. It was phreatomagmatic, a catastrophic interaction between fire and water that multiplied the force exponentially. Within seconds, the pressure wave tore through the ocean above. The surface didn't ripple, it erupted upward in a column of superheated steam, ash, and pulverized rock. The initial plume punched through the troposphere in minutes, reaching an altitude of 58 kilometers. To put that in perspective, commercial aircraft cruise at roughly 10 to 12 kilometers. The plume rose nearly 5 times higher. It entered the mesosphere, region of the atmosphere so high that meteors burn up there. A place where the air is too thin for conventional weather, where the boundary between Earth's atmosphere and space begins to blur. No volcanic plume in the modern era of satellite observation had reached such heights. But the plume was only the most visible consequence. The explosion generated a pressure wave, a sonic boom of such magnitude that it propagated through the atmosphere like a stone thrown into still water, ripples expanding outward in all directions. Barometric sensors in New Zealand, nearly 2,400 kilometers away, registered the wave within hours. In Australia, weather stations recorded anomalous pressure spikes. In Japan, instruments detected the disturbance crossing the Pacific. And then something extraordinary happened. The pressure wave circled the entire planet. Once, twice, satellites tracking atmospheric conditions documented it passing the same points multiple times over the following days as it reverberated through the global atmosphere. It was detectable everywhere. From the Amazon to Siberia, from coastal cities to remote research stations in Antarctica. The sound itself was heard across vast distances. In Fiji, more than 750 kilometers away, people described a deep rumbling like distant thunder that went on and on. In Alaska, over 9,000 kilometers from the eruption, sensitive microphones picked up the infrasonic waves sound too low for human ears but powerful enough to travel halfway around the world. It was the loudest natural event recorded on Earth since the eruption of Krakatoa in 1883. But sound was not the only thing traveling outward from Hunga Tonga. The explosion had displaced an enormous volume of water. The ocean above the caldera had been thrust upward and outward with tremendous force, and as it collapsed back it generated waves. Tsunami waves. Within minutes, the first waves radiated outward from the volcano in concentric circles. Unlike earthquake-generated tsunamis, which result from vertical displacement of the seafloor, these waves were born from an explosion, a different mechanism, but no less dangerous. The waves moved at speeds exceeding 800 kilometers per hour in deep water. As they approached shallow coastlines, they slowed and grew taller, concentrating their energy. Tonga's outer islands were struck first. Waves up to 15 meters high crashed onto shores with almost no warning. Coastal villages were inundated. Homes built near the waterline were swept away. Communication cables connecting Tonga to the outside world were severed. Within an hour, the nation was cut off. No internet. No international phone lines. The world knew something catastrophic had happened. Satellite imagery showed the massive plume, the expanding pressure waves, but from Tonga itself, there was only silence. The tsunami continued outward. It reached Fiji and Samoa within hours. Coastal areas in New Zealand and Australia issued evacuation orders as waves arrived. Smaller but still dangerous, up to 2 meters in some locations. Across the Pacific, from Japan to California to Chile, tide gauges registered the waves. Harbors were emptied as a precaution. Boats were moved to deeper water. Communities that had not thought about tsunamis in years suddenly remembered the ocean's power. In Japan, waves over a meter high arrived at the coast. In California, surges damaged harbors and marinas. In Peru, 2 people lost their lives when an unexpected wave struck a beach. The tsunami had crossed the entire Pacific Ocean, more than 10,000 kilometers in some directions, still carrying enough energy to be lethal. Back at the volcano, the eruption continued for hours. Not with the same catastrophic intensity as the initial explosion, but with sustained violence. Ash and steam poured into the sky. Lightning flickered through the plume as static electricity built up in the churning particles. By nightfall, the eruption had reshaped the islands entirely. Where there had been a single landmass connecting Hunga Tonga and Hunga Haʻapai, there was now open water once more. The island that had slowly emerged in 2014 was gone, vaporized, obliterated down to the waterline and below. The caldera had partially collapsed inward, and the ocean had reclaimed what the volcano had briefly built. What remained above water were only fragments of the original islands, smaller now, scarred and steaming, surrounded by a sea turned murky with suspended ash and debris. The earth had spoken, and the world had listened. In the immediate aftermath, there was confusion. The scale of what had happened was not yet clear. Satellite images showed an enormous ash cloud spreading across the South Pacific, but the details beneath remained obscured. Tonga itself had gone silent, the undersea communications cable severed, power grids damaged, communities isolated. For the first 24 hours, the world knew only fragments. Aid organizations mobilized without full information. Military reconnaissance aircraft were dispatched from New Zealand and Australia, flying over the affected areas to assess the damage from above. What they reported was sobering. Entire coastal villages buried under ash. Forests stripped bare by the tsunami. Infrastructure destroyed. And a fine gray powder covering everything: roofs, roads, water supplies, rendering much of it unusable. Ash, in the aftermath of an eruption, is not merely a nuisance. It is abrasive, toxic to breathe in concentration, and when mixed with water, it becomes corrosive. It contaminates drinking water. It smothers crops. It turns rain into a caustic slurry that damages whatever it touches. The island of Tonga Tapu, home to most of Tonga's population, had been blanketed with several centimeters of ash. Gardens were ruined. Rainwater collection systems critical in a nation of small islands were compromised. And beneath the practical concerns was the psychological weight. The sound of the explosion had been heard across the archipelago. The tsunami had come without the usual warning signs. People had run to higher ground in darkness, not knowing if the waves would stop or continue through the night. 3 Tongan lives were lost. A number that might seem small in the context of historical volcanic disasters, but each one a person with a name, a family, a place in their community. 2 were swept away by the tsunami on the island of Mango. Another, a British national, was killed while trying to rescue her dogs as the waves approached. In a nation of just over 100,000 people, the loss resonated deeply. But Tonga was not alone in experiencing consequences. As the days passed and scientists analyzed the data streaming in from monitoring stations worldwide, the true scope of the eruption began to emerge. The explosion had released approximately 400,000 times the energy of the atomic bomb dropped on Hiroshima. It had injected an estimated 146 million tons of water vapor into the stratosphere, the largest injection of water into that atmospheric layer from a single event in recorded history. This was significant for reasons that took time to appreciate. Most volcanic eruptions cool the planet temporarily. They inject sulfur dioxide into the stratosphere, which forms tiny droplets of sulfuric acid that reflect sunlight back into space. After the eruption of Mount Pinatubo in 1991, global temperatures dropped by about half a degree Celsius for 2 years. But Hunga Tonga was different. It erupted underwater, which meant much of its sulfur was dissolved into seawater rather than reaching the stratosphere. Instead, the eruption sent up vast quantities of water vapor, a greenhouse gas. Scientists calculated that the water vapor could remain in the stratosphere for years, potentially contributing to a slight warming effect rather than cooling. It was a reminder that even in an age of advanced monitoring, volcanic eruptions can still surprise us. The Earth does not always follow the patterns we expect. In Japan, atmospheric sensors detected pressure waves arriving and then circling back around the planet. Meteorologists watched as the shockwave created unusual cloud formations, distorting weather patterns thousands of kilometers from the eruption site. In the Caribbean, tide gauges registered small but measurable waves hours after the eruption, not from the tsunami traveling through the ocean, but from atmospheric pressure waves pushing down on the sea surface as they passed overhead. It was a phenomenon called a media tsunami, and it demonstrated just how interconnected the Earth's systems are. An eruption in the South Pacific could create waves in the Caribbean, not through water, but through air. The eruption had become a global experiment in atmospheric science, oceanography, and planetary connectivity. But while scientists marveled at the data, the people of Tonga faced more immediate realities. International aid began arriving within days. New Zealand and Australian military aircraft landed with emergency supplies, water, food, tarps, medical equipment. But delivering aid was complicated by the ash. Runways had to be cleared repeatedly. Drinking water had to be shipped in, as local supplies were contaminated. Slowly, communication was restored. Temporary satellite links allowed families to contact loved ones abroad. The full picture of the damage became clearer, though not less daunting. Rebuilding would take years. Some of the smaller islands had been rendered uninhabitable, their freshwater sources destroyed by saltwater inundation and ash contamination. Families would need to relocate. Communities would need to be reimagined. And hanging over everything was a question that no one could answer with certainty. Would the volcano erupt again? The collapse of the caldera suggested that much of the pressure had been released. But volcanic systems are not simple machines that empty and then refill on predictable schedules. Magma chambers are complex, multi-layered, fed by conduits from deep within the mantle. What had erupted in January might have been only a portion of the available magma. Or it might have been everything. Only time would tell. Monitoring equipment was re-established as quickly as possible. Seismometers to detect ground movement, gas sensors to measure emissions, satellite observations to track any changes in the volcano's shape or temperature. The vigilance would continue. Because the one certainty about volcanic systems is that they are never truly finished. They rest. They wait. They accumulate energy in darkness and silence. And sometimes they wake again. Volcanic eruptions, for all their immediate drama, are also invitations to look backward. Every caldera tells a story written in layers of ash and stone. Every submerged crater holds evidence of eruptions that happened before human witnesses existed to record them. Hunga Tonga Hunga Haʻapai was not erupting for the first time in 2022. It was simply the first time in the modern era that we had the instruments to measure it fully. Geologists studying the region have found evidence of significant eruptions occurring roughly every 1,000 years. Ash deposits on nearby islands. Tsunami sediments in coastal strata. The geological record, read carefully, reveals a pattern of periodic violence stretching back millennia. The caldera itself, that 5-kilometer-wide depression beneath the waves, was created by an ancient collapse. Likely tens of thousands of years ago, a massive eruption emptied the magma chamber so quickly that the overlying rock had nothing to support it. It fell inward, creating the bowl-shaped structure that persists today. What we witnessed in January 2022 was not the creation of something new, but the reawakening of something very old. This perspective matters because it changes how we understand risk. In human terms, 1,000 years feels like forever. Civilizations rise and fall in shorter spans. Languages evolve. Technologies transform beyond recognition. A volcanic system that erupts once per millennium seems almost theoretical, a geological abstraction rather than an immediate concern. But the Earth does not measure time the way we do. For a volcano, 1,000 years is merely the interval between breaths. A pause, not an ending. And in the Pacific, there are dozens of volcanic systems like Hunga Tonga. Some monitored closely, others barely studied. Some with recent histories of activity, others quiet for so long that nearby populations have forgotten they are volcanoes at all. The challenge facing modern volcanology is not a lack of knowledge, though there is always more to learn, but rather the difficulty of maintaining vigilance across such vast timescales. We are a species adapted to immediate threats. The predator in the tall grass. The storm on the horizon. Our nervous systems evolved to respond to dangers that unfold in seconds or hours, not centuries. Yet volcanic risk operates on those longer timescales punctuated by sudden violence. Krakatoa erupted catastrophically in 1883, killing tens of thousands and affecting global climate. Then it went quiet for decades. Today, Ana Krakatoa, child of Krakatoa, grows in the same caldera, a new volcanic cone building where the old one destroyed itself. Mount Vesuvius buried Pompeii in 79 AD, preserving the city in ash and creating one of archaeology's most haunting records. The volcano has erupted dozens of times since most recently in 1944. Today, more than 3 million people live within its potential blast radius. These are not abstract risks. They are ongoing relationships between human populations and geologic forces that operate on their own timelines. What Hunga Tonga demonstrated in 2022 was that even relatively remote volcanoes far from major population centers, in the middle of the ocean, can have global consequences. The pressure wave that circled the planet. The tsunami that reached distant coastlines. The water vapor injected into the stratosphere, potentially influencing climate patterns for years. Distance in the modern interconnected world offers less protection than it once did. Stories like this are not meant to be rushed. They are meant to be followed by those who still listen, by those who understand that the Earth operates on scales both intimate and vast. If this journey resonates with you, you are already part of Fury of the Earth, walking alongside forces that have shaped this planet long before us and will continue long after. The question facing scientists and policymakers is how to prepare for events that are both inevitable and unpredictable. We know certain volcanic systems will erupt again. The geological evidence is clear. But we cannot say with precision when, tomorrow, next year, 3 centuries from now? This uncertainty complicates planning. Resources are finite. Attention is limited. It is difficult to maintain emergency preparedness for an event that might not occur within any living person's lifetime. Yet when it does occur, as it did at Hunga Tonga, the consequences unfold with ruthless speed. The eruption itself lasted hours. The tsunami waves traveled for a day. But the impacts, social, economic, environmental, will persist for years, perhaps generations. This is the temporal paradox of volcanic risk. Preparation measured in decades. Events measured in hours. Consequences measured in lifetimes. And beneath it all, the slow accumulation of magma. The gradual increase in pressure. The patient, inexorable processes that build toward the next release. The Earth, as always, remembering. In the weeks following the eruption, scientists from around the world turned their attention to Hunga Tonga with renewed intensity. Not simply to understand what had happened, but to learn what such events could teach us about prediction, preparation, and the limits of our monitoring capabilities. The data was extraordinary. Never before had a volcanic eruption of this magnitude been so thoroughly documented by modern instruments. Satellites had captured the explosion in real time. Seismometers on every continent had recorded the pressure waves. Ocean buoys had tracked the tsunami as it propagated outward. Yet for all this technological sophistication, the eruption had not been predicted with any meaningful precision. The warning signs were there, certainly. The increased seismic activity. The smaller eruptions in the days before. But these same signs appear at dozens of volcanoes every year, most of which do not proceed to catastrophic eruption. This is the central challenge of volcano monitoring, distinguishing between normal unrest and the precursors to disaster. A volcano can show signs of activity for months or even years without erupting. Magma can rise, pressurize the system, then cool and solidify without ever reaching the surface. Earthquakes can cluster and then dissipate. Gas emissions can increase and then stabilize. The systems are complex, influenced by factors we can measure: temperature, pressure, gas composition, and factors we cannot easily observe, such as the internal structure of magma chambers and the network of fractures through which magma travels. It is not unlike trying to predict exactly when an avalanche will occur on a snow-covered mountain. You can assess the conditions, you can identify when the slope is unstable. But the precise moment of failure, the specific trigger, often remains elusive until it happens. At Hunga Tonga, the monitoring network was modest compared to more heavily studied volcanoes. The remoteness of the location made continuous observation difficult. There were seismometers on nearby islands, but not on the volcano itself. Satellite observations provided valuable data, but with limitations, clouds could obscure the view, and satellites only pass overhead periodically, not continuously. In the aftermath, scientists recognized what they had witnessed was an eruption style that remains poorly understood: the explosive interaction between magma and seawater at great depth. Phreatomagmatic eruptions had been documented before, but rarely at this scale. The mechanics are brutally simple in concept. Superheated rock meets water. Water flashes to steam, the volume expansion generates enormous pressure. But the details are devilishly complex. How much water must interact with how much magma to generate an explosion of this magnitude? What role does the depth of water play? How does the geometry of the caldera influence the explosive potential? These are questions that cannot easily be answered in laboratory settings. The pressures and temperatures involved are too extreme. The scale's too large. Instead, scientists must study the geological record, examine the deposits left by ancient eruptions, and develop computer models to simulate the physics involved. Since the eruption, research teams have been analyzing every available piece of data. Satellite measurements of the plume height and expansion rate. Infrasound recordings that captured the low-frequency sound waves. Atmospheric pressure readings from thousands of stations worldwide. Each dataset adds another piece to the puzzle. One of the most significant findings has been the unprecedented amount of water vapor injected into the stratosphere. Initial estimates suggested roughly 10% of the water normally present in that atmospheric layer was added in a single day. This has climate scientists paying close attention. Water vapor at such altitudes can persist for years. potentially affecting global temperature patterns in ways that are still being calculated. It is a reminder that volcanic eruptions are not merely local events. They are planetary phenomena capable of altering atmospheric chemistry, ocean circulation, and climate systems across hemispheres. The eruption has also prompted discussions about improving monitoring networks in remote volcanic regions. The Pacific is dotted with underwater volcanoes' seamounts, many of which are active or potentially active. Most are unmonitored. Some are not even fully mapped. We know more about the surface of the moon than we do about the deep ocean floor in many regions. And yet these underwater systems pose real risks. Not just from eruptions themselves, but from the tsunamis they can generate and the atmospheric effects they can produce. There are proposals now for expanding networks of ocean bottom seismometers, deploying more sophisticated satellite monitoring systems, and developing better models for predicting freedomagmatic eruptions. But these efforts require resources, political will, and international cooperation. Volcanoes do not respect borders. An eruption in Tonga affects coastlines around the Pacific. A volcanic winter triggered by a massive eruption anywhere on Earth would affect everyone. The question is whether we will invest in preparation during the quiet periods, or wait until the next catastrophe forces our attention. Hunga Tonga has provided a stark reminder that the quiet periods do not last forever. Somewhere, at this very moment, magma is rising beneath another volcano. Pressure is building. Gases are accumulating. The Earth continues its ancient work, indifferent to our preparedness or lack thereof. All we can do is watch, measure, and try to understand. And hope that when the next volcano speaks, we are listening carefully enough to hear the warning. Months after the eruption, life in Tonga began the slow process of returning to a new normal. Not the normal that existed before January 15th. That world was gone, buried under ash or swept away by waves. But a new equilibrium built upon what remained and what could be rebuilt. The physical scars were everywhere. Coastlines reshaped by the tsunami. Villages that would need to be relocated entirely. Agricultural land rendered sterile by salt and ash, requiring years to recover. Coral reefs damaged by the pressure wave and subsequent sedimentation. The island of Mango, which lost 2 residents to the tsunami, was largely abandoned. The freshwater sources had been contaminated. The risk of remaining, should another event occur, seemed too great. Other communities face similar calculations. How do you rebuild in the shadow of a volcano that has demonstrated such power? How do you plant crops in soil that may take a generation to heal? How do you explain to children that the ocean, which provides so much, can also take everything away? These are not merely practical questions, they are existential ones. For many indigenous Pacific peoples, the relationship with the land and the sea is not transactional. It is ancestral. Identity is tied to place in ways that people from more mobile societies sometimes struggle to comprehend. To leave an island is not simply to relocate. It is to sever connections that have persisted for centuries, to abandon graves, to break the continuity between past and future. Yet staying carries its own costs. The Tongan government, with support from international partners, has faced the difficult task of balancing cultural preservation with physical safety. Some communities have chosen to rebuild in place, accepting the risk. Others have made the painful decision to relocate to higher ground or to different islands entirely. There is no perfect answer. Only choices that carry different burdens. The economic impact has been substantial. Tourism, a vital source of income, was disrupted for months. Fishing communities lost boats and equipment. The undersea communications cable, which took 5 months to repair, left the nation digitally isolated during a period when connection to the outside world was desperately needed. Aid arrived, but aid is temporary. It addresses immediate needs: food, water, shelter, but it does not replace livelihoods. It does not restore the fishing grounds. It does not bring back the crops that were buried. Recovery in the truest sense is measured in years. Children who experience the eruption and tsunami will carry those memories into adulthood. The sound of the explosion. The sight of the ash cloud. The terrifying rush to higher ground as the ocean withdrew before the waves arrived. Trauma, like ash, settles into places that are not immediately visible. Psychologists working with affected communities have noted the signs: anxiety triggered by loud noises, reluctance to sleep near the coast, children who wake from nightmares of rising water. These wounds do not appear on damage assessment reports. They do not show up in satellite imagery, but they are real and they persist. And yet, alongside the trauma, there is also resilience. Communities that came together in the immediate aftermath have maintained those bonds. Neighbors who helped clear ash from each other's roofs continue to support one another. Families separated by distance have found ways to stay connected, even with limited communication infrastructure. There is something profoundly human in the way people respond to disaster. The capacity to adapt, to find meaning in survival, to rebuild not just structures but hope. In the months following the eruption, stories emerged of remarkable acts of courage and compassion. The man who used his boat to evacuate neighbors as the tsunami approached. The community that shared its water supplies with those whose sources had been contaminated. The children who helped plant new gardens in soil that was slowly recovering. These stories do not erase the loss, but they provide a counterweight to despair. Volcanic eruptions remind us of our fragility, but human response reminds us of our strength. The Tongan people have lived with volcanic risk for as long as they have inhabited these islands. Their ancestors witnessed eruptions, survived tsunamis, rebuilt after disasters whose details are now lost to time but whose existence is recorded in oral histories and geological strata. This is not the first time these islands have faced such forces, and it will not be the last. But each generation must learn anew how to live with such power nearby. How to respect it without being paralyzed by fear. How to prepare while still planting gardens and building homes and raising children with hope for the future. It is a balance that has no formula. Only practice. In Nuku'alofa, the capital, life has returned to a rhythm that resembles normalcy. Markets are open. Schools are teaching, the harbor, cleared of debris, hosts fishing boats once again. But the volcano remains. Visible on clear days from certain vantage points, its remnants still steam occasionally, reminding anyone who looks that direction that the Earth's work is never truly finished. Monitoring equipment continues to record. Seismometers listen for tremors. Satellites watch for changes in temperature or shape. The vigilance is permanent now. A recognition that living in such a place requires awareness, preparation, and a kind of courage that those in geologically stable regions may never need to cultivate. The people of Tonga have that courage. Not because they are exceptional, but because they have no choice. The volcano is their neighbor, unpredictable, powerful, and patient. And they will continue to live beside it, as their ancestors did, with respect and caution and the stubborn determination to call these islands home. Step back far enough, and even the most violent eruption becomes part of a larger pattern. Hunga Tonga was extraordinary by human measures, the sound heard across hemispheres. The tsunami that crossed an ocean, the atmospheric shockwave that circled the planet twice. But in the geological history of Earth, it was moderate. Significant, yes. Historic for our era. But not unprecedented in the long chronicle of volcanic events that have shaped this world. The planet has witnessed far larger eruptions. Events so massive that they altered the course of evolution itself. 74,000 years ago, Mount Toba in Indonesia erupted with a force that dwarfed anything in recorded human history. The explosion ejected roughly 2,800 cubic kilometers of material into the atmosphere. Ash fell across the Indian subcontinent. Global temperatures dropped by several degrees for years, possibly triggering a volcanic winter that lasted a decade or more. Some scientists believe this eruption created a population bottleneck in early human populations. Though we are all descendants of the few thousand individuals who survived that catastrophic period. It is impossible to verify with certainty, but the genetic evidence is suggestive. Humanity passed through a narrow passage in those years and emerged on the other side diminished in number, but equipped perhaps with the adaptability that would eventually allow us to spread across every continent. 252 million years ago, volcanic eruptions in what is now Siberia released enough greenhouse gases to warm the planet dramatically. Ocean chemistry changed. Oxygen levels dropped. Roughly 90% of marine species and 70% of terrestrial species went extinct in what geologists call the Permian-Triassic extinction event. The Great Dying, it was not a single eruption but a series spanning perhaps 2 million years. Lava flows covering an area larger than Europe. Gases released from those flows altering the atmosphere so profoundly that the world became nearly uninhabitable. Life survived, but it took millions of years for ecosystems to recover their complexity. These are the benchmarks against which we measure volcanic risk. Not the eruptions we have witnessed in modern times, but the ones written into stone and bone and the genetic code of surviving species. Hunga Tonga was nowhere near that scale. But it reminded us that the machinery capable of such events still operates beneath our feet. The Pacific Ring of Fire, where Hunga Tonga sits, is the most volcanically active region on Earth. It traces the boundaries of the Pacific Plate, where subduction zones encircle the ocean like a jagged necklace. From Chile to Alaska, Japan to New Zealand, Indonesia to the Philippines, hundreds of active volcanoes mark the places where oceanic crust descends into the mantle and magma rises in response. This is not a collection of isolated threats. It is a connected system, driven by the same fundamental process. Plate tectonics. The slow convective churning of the Earth's interior, which moves continents over millions of years and builds mountains from ocean floors. Volcanoes are the visible symptoms of those deeper processes. The release valves. The places where internal heat and pressure find pathways to the surface. And they will continue as long as the Earth's interior remains hot. As long as radioactive decay generates heat deep within the planet. As long as the core and mantle convect and drive the motion of crustal plates. Which is to say, for billions of years yet. We live on a geologically active planet. It is easy to forget this during the long quiet periods. When years pass without a major eruption. When the ground feels solid and unchanging beneath our feet. But the quiet is temporary. Always. Understanding this does not require fear. But it does require perspective. We build our cities and plant our crops and raise our families on a planet that is still forming itself. The mountains rising, the ocean floors spreading, the continents drifting at the speed fingernails grow. From a human perspective, these changes are invisible. From a geological perspective, they are rapid. We exist in the narrow slice of time between what the Earth was and what it will become. And during that slice, we must navigate the forces that continue to reshape the world around us. Volcanic eruptions are part of that navigation. Not aberrations, but features of the landscape we inhabit. Some volcanoes we can monitor closely. Others remain remote and poorly understood. Some will erupt within our lifetimes. Others will sleep through generations. But the question is never whether volcanoes will erupt again. Only when. Only where. And whether we will be prepared when they do. The eruption at Hunga Tonga provided valuable lessons about the limits of our prediction capabilities. About the global reach of even moderate eruptions. About the resilience required to live alongside such forces. Those lessons, if heeded, may save lives when the next volcano awakens, and there will be a next one. Somewhere on the Ring of Fire, or along the volcanic arcs of the Mediterranean, or beneath the ice of Antarctica, or in one of the countless underwater systems we have barely begun to map. Magma is rising somewhere at this very moment. Pressure is building. Gases are accumulating in chambers that have been sealed for decades or centuries. The Earth does not rest. It only pauses between breaths, and when it breathes again, we will feel it. The question is whether we will have learned enough from Hunga Tonga and all the eruptions that came before to meet that moment with preparation rather than simply surprise. The planet offers no guarantees. Only patterns, only probabilities. And the certainty that what seems solid is, on geological timescales, fluid. What seems permanent is temporary. What seems quiet is often only resting. The Earth, as always, remembering its own nature. There is a photograph taken from space a few days after the eruption. It shows the South Pacific vast and blue, with a discolored patch spreading outward from where Hunga Tonga once stood. Not the dramatic plume of the eruption itself, but the aftermath ash and pumice floating on the surface, drifting with the currents, dispersing slowly across hundreds of kilometers. From that altitude, the ocean looks peaceful, almost serene. But the photograph captures something important. It shows how far the consequences of a single moment can travel, how an explosion lasting minutes can alter water chemistry for months, how particles suspended in seawater can affect marine ecosystems far from their source. The eruption is over. The immediate danger has passed. But the effects continue, subtle and pervasive, touching systems and places that seem unconnected to a volcanic island in the South Pacific. This is the nature of planetary events. They do not conclude neatly, they echo forward through time. Scientists studying the stratospheric water vapor injected by Hunga Tonga have found it dispersing across both hemispheres. Satellite measurements show elevated water vapor levels at altitudes where it normally appears only in trace amounts. The climate effects remain uncertain. Models suggest a slight warming influence, but the magnitude and duration are still being calculated. It may be years before we fully understand how this single eruption affected global temperature patterns, cloud formation, and atmospheric circulation. Meanwhile, in Tonga, the work of recovery continues. New homes have been built, gardens replanted, communication systems restored. Children who evacuated to higher ground during the tsunami have returned to schools rebuilt on foundations that stand a little higher, a little farther from the shore than before. The physical rebuilding is visible. The psychological rebuilding is quieter, measured in conversations rather than construction, in the gradual return of routines that provide structure and comfort. Communities have not forgotten what happened, but they have learned to live alongside the memory, which is different than being defined by it. This is resilience, not the absence of fear, but the ability to function despite it. Not the erasure of trauma, but the integration of difficult experiences into a life that continues forward. The volcano itself remains quiet. Steam occasionally rises from vents on what little land surface remains above water. Seismometers detect small tremors, periodically micro-earthquakes that indicate ongoing geological activity at depth, but nothing approaching the intensity that preceded the January eruption. Monitoring continues. Scientists check the data daily. Satellites pass overhead on regular orbits. Thermal cameras searching for changes in temperature that might indicate rising magma. The vigilance has become routine, part of the ordinary background of life in the region. And perhaps that is how it should be. Not constant alarm, but sustained awareness. Recognition that the ground beneath our feet is not as solid as it feels. That the ocean, for all its beauty, carries forces we cannot fully control. We have built a civilization on the assumption of stability. Our cities presume the coastline will remain where it is. Our infrastructure assumes the ground will not suddenly shift. Our agricultural systems depend on predictable seasons and stable climate patterns. But the Earth offers no such guarantees. It moves on timescales we struggle to comprehend. It operates according to physical laws that care nothing for human convenience. And occasionally it reminds us of this fact with sudden, overwhelming force. The eruption at Hunga Tonga was one such reminder, not the largest, not the deadliest, but significant enough to command global attention. Powerful enough to be felt, quite literally, around the world. And in that moment of planetary awareness, perhaps there was also an opportunity to recognize our shared vulnerability, to understand that geological forces do not respect national borders or political divisions. A volcanic eruption in the South Pacific creates tsunamis that reach Japan and Chile. Atmospheric shock waves that circle the globe. Climate effects that touch every continent. We are connected, whether we acknowledge it or not, by the planet we inhabit. The forces that shape the Earth, volcanism, plate tectonics, atmospheric circulation, ocean currents operate on scales larger than any individual nation or culture. They remind us that for all our technological sophistication, we remain subject to processes we can measure but not control. This is not a cause for despair. It is simply a fact. And facts, acknowledged clearly, can guide better decisions. We can improve monitoring systems. We can develop more accurate models. We can build infrastructure designed to withstand the forces we know will eventually arrive. We can plan for the long term, even when the political and economic systems we have created incentivize focus on the immediate. And we can remember that we are not the first generation to face these challenges, nor will we be the last. Our ancestors survived volcanic winters and tsunamis with far less technology and far less understanding. They adapted. They persisted. They passed forward the accumulated knowledge that allows us to stand here now, looking back at what happened and forward to what might come. We owe them the same effort, the same commitment to learning, preparing, and passing forward what we have discovered. The planet will continue its ancient rhythm long after we are gone. Continents will drift. Mountains will rise and erode. Volcanoes will build themselves and then collapse over and over in the slow pulse of geological time. Our species occupies a brief moment in that immense span, but it is our moment, and how we navigate it matters. Not to the Earth, which will endure regardless, but to the generations that follow us, to the children being born today who will inherit whatever world we leave them. If you wish to keep walking beside these powerful forces, to remain attentive to the planet's unfolding story, subscribe to Fury of the Earth. Join us in bearing witness to the extraordinary processes that shape our world, the volcanoes, and earthquakes, the storms and floods, the slow patient work of erosion, and the sudden violence of tectonic release. These are not merely disasters. They are the mechanisms by which the planet renews itself, the forces that built the mountains we climb and carved the valleys where we live. Understanding them does not eliminate the danger, but it provides context, perspective, and perhaps in time the wisdom to live more carefully on a world that is always in its own way alive. The Earth remembers, and so must we.